So let's do that for this particular case. So we're going to assume we're going to have an electron in the n equal 1 state of the hydrogen atom, which, by the way, we call this the ground state. Whenever we have an electron in the lowest possible state, we say it's in the ground state. And then when that electron gets promoted to a higher shell, say the n equal 2, it could also be the n equal 3, that's also a higher state. Whenever this happens, when the electron is in a higher energy state, we say that that hydrogen atom, or the electron as well, is in an excited state. And there's, of course, a variety of excited states that can exist because there's a whole bunch of these higher energy shells that exist above the n equal 1 ground state. But nevertheless, we calculated this energy difference between the n equal 1 and the n equal 2 state, and we calculated that to be 1.635 times 10 to the negative 18 joules. We calculated that in this particular step here. And we can set this energy equal to this Planck's constant times the speed of light divided by the wavelength of the photon that's going to need to come in here and get absorbed to cause this particular transition to happen. If we do a little bit of algebra here, multiply both sides by lambda and divide both sides by delta E, we see that we can calculate the wavelength of the photon that's going to need to cause this particular transition. That's going to be Planck's constant times the speed of light divided by the change in energy between these two particular states. So let's do this calculation. All right, my wavelength, that's going to have to be Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. We're going to multiply that. That's Planck's constant. We're going to multiply that by the speed of light in a vacuum, 3 times 10 to the 8th meter for every second. And we're going to divide that by the difference in energy between the two states, right here, 1.635 times 10 to the negative 18 joules. All right, let's check our units first. A joule on the numerator cancels a joule on the denominator. On the numerator, if we take a regular second and multiply that by an inverse second, they cancel. And we see that the unit we're left with is a meter, and that makes me happy because I'm looking for a wavelength. Now we'll do the numerical portion of the calculation. 6.626 times 10 to the negative 34 times 3 times 10 to the 8th, and we're going to divide that by 1.635 times 10 to the negative 18. That's a tiny number. Let's see. 1, 2, 3, 4, 5, 6, 7. I'm getting 1.22 times 10 to the negative 7 meter. Watch this again. 1, 2, 3, 4, 5, 6, 7. And I rounded that one up right there. So it's 1.22 times 10 to the negative 7 meter, which we can convert this to nanometers if we remember. Let's go ahead and do that. I'm going to put my base unit here, the meter, and then I remember that goes deci, centi, milli, double dash, micro, double dash, nano. And in the meter position, we have this particular number here. And we're going to move, to go from meter to nanometer, we're going to move 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces in this direction. So of course I move my decimal 9 spaces in this direction. 1, 2, 3, 4, 5, 6, 7, 8, 9. 121.5, 122 nanometers. And so what we've done now is we have calculated the wavelength of a photon that would be required to take an electron in the ground state of the hydrogen atom, the n equal 1 shell. That photon, if we shine in a photon at 122 nanometers, that's going to be ultraviolet light. that's going to promote that electron to the n equal 2 state. The opposite can happen too. This electron, now that it's in the n equal 2 state, it can release the photon at 122 nanometers and drop back down to the n equal 1 state. And I want to do that calculation for, let's do this particular transition is what we'd call it. Let's calculate this for the, let's take the n equal 3 state of the hydrogen atom. We got an electron there. And we're going to have that electron drop, not to the ground state, but we're going to take it to the n equal 2 state of the hydrogen atom. And of course, as it loses this energy, it's going to release a photon. Sometimes we write a photon as h nu, because the energy of a photon is h nu. So sometimes we just write it like that. So let's calculate the energies of the photon that would be released when an electron in the hydrogen atom goes from the n equal 3 excited state of the hydrogen atom to the n equal 2 excited state of the hydrogen atom. And then after we calculate that energy, we're going to use this equation, E equals hc over lambda, which can also be written as lambda is hc over E, to calculate the wavelength of the photon that would be emitted during this particular transition. So we need to calculate the difference in energy between these two states, which of course is always the final state minus the initial state. In this case, the final state will be the energy of the second shell, because that's where we're ending up. And we're going to subtract from that the energy of the initial shell, which is E3. So let's see, delta E, that's going to be E2, which will be EH over 4, because it's 2 squared, minus EH over 9, because it's 9 squared, where we remember that EH is negative 2.18 times 10 to the negative 18 joules. Now we can factor out EH from this particular equation here. So let's do that. So delta E, we factor out the EH, and that if we do that, it's going to be a quarter minus 1/9. So this is the equation that we're going to solve. So let's see, I got my change in energy for this process. That's going to be negative 2.18 times 10 to the negative 18 joules. That's my EH. And we're going to multiply that by a quarter minus a 1/9. Well, a quarter, that's just 0.25. Let's see, 0.25 minus 1/9, that's just 0.11111. That's 0.139. If I did my math right. And let's see, that's positive, isn't it? And in this case, we have a negative times a positive, so that's going to give me a negative value. Delta E is negative this times this, so let me do this multiplication, 0.139 times 2.18 times 10 to the negative 18, 3.03 times 10 to the negative 19. That's the change in energy as an electron goes from the n equal 3 down to the n equal 2 shell of a hydrogen atom. And this just means that the hydrogen atom, the negative sign means that the hydrogen atom loses energy when it undergoes this transition. Well, that energy's got to go somewhere, and where it goes is into a photon that's released. And we can calculate now the energy of, the wavelength of that particular photon using this equation here. We just calculated the change in energy. We know these two constants. Just like before, we can calculate the wavelength. Let's do that. We'll set it up here. So let's see, the wavelength, that's going to be Planck's constant times the speed of light in a vacuum And we're going to divide that by our energy that we just calculated, 3.03 times 10 to the negative 19 joules. This is the energy of the photon, which is going to be a positive energy. That's why I've dropped the negative sign. Oh, and I forgot my units here on Planck's constant. That should be joules times seconds. All right, the joule on the numerator cancels the joule on the denominator. The second on the numerator cancels the inverse second on the denominator, and we have lambda in units of meters, just like before. Now we'll do the calculation with the numerical portion. 6.626 times 10 to the negative 34. We're going to multiply that by 3 times 10 to the 8, and we're going to divide that by 3.03 times 10 to the negative 19. Let's see. 1, 2, 3, 4, 5, 6, 7. 6.56 times 10 to the negative 7 meters. What's that value in nanometers? Well, once again, if we go through the process, let's do that up here. Our base unit is meter. Deci, centi, milli, double dash micro, double dash nano. We have this value starting here at the meter. We want to convert that to nanometer. I've got to move 9 spaces. Remember, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm going to move my decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 656 nanometers. Boy, that number's familiar, isn't it? I remember that number from somewhere. That's right. This is the wavelength of light that the hydrogen atom gives off, or one of the wavelengths of light that the hydrogen atom gives off. You might remember that, 656 nanometers, that's one of the wavelengths of light that gives off. It's actually red light. And so what we found is that if we go from the n equal 3 state to the n equal 2 state of the hydrogen atom, when this electron drops from the n equals 3 to the n equals 2 level, a red photon is given off. That red photon at 656 nanometers, that exactly matches the wavelength of light that's given off by a hydrogen atom. In a similar way, you can find, if you do the calculations, and you should do this, that if an electron drops from the n equals 4 to the n equals 1 level of the hydrogen atom, it's going to give off a wavelength of light that corresponds to 486 nanometers, which again, that exactly corresponds to the wavelength of light that's given off by a hydrogen atom when it gets excited. And we can continue this process. If we have an electron in the n equal 5 level, and that electron drops to the n equal 2 level, when it does that, it's going to give off a photon with a wavelength of light that's 434 nanometers. And you should be able to do the calculations that show that these are indeed the case. And it does turn out that the colors of light that hydrogen gives off when it's excited and it releases electrons, if it drops from a higher energy shell to the n equal 2 shell, this tends to give off light in the visible region, and so these are photons of light that we can see. So the Bohr model of the atom has this basic idea, this basic structure, where you have a solid, dense nucleus, and the electron is usually in the ground state n equal 1 level. Of course, we can calculate this energy. And then there are higher energy shells. If the electron goes into one of these higher shells, we say that the electron is in an excited state. And there's several of these higher state shells. They run all the way up to n equals infinity. But by calculating the difference in energies between these various shells that the electrons can move between, we can actually get some insight into the colors of light that hydrogen either emits or absorbs.